Hi everyone. This is our look at enthalpy change. This is our second big calculation in the thermochemistry unit, and we did actually see this formula once upon a time way back in grade 10 as well. The first thing to say is an enthalpy change, it represents a change in potential energy. This is a really important contrast with Q equals mc delta T. A temperature change was associated with a change in kinetic energy. But here, there is no temperature change, and it represents something about the potential energy. This can happen in a couple of different ways. It's the kind of energy change that happens during a chemical reaction, combustion, neutralization, formation, any kind of chemical reaction, or also a phase change, melting, freezing, boiling, condensing, and even dissolving. These types of situations represent a change in potential energy because they're all about breaking and forming chemical bonds. These bonds might be intramolecular in a chemical reaction, ionic or covalent bonds, and they represent a change in intermolecular bonds during a phase change. So there's something about bond energy here as well, but the more important connection to make is enthalpy change is represented, it's a kind of potential energy change. Here's the formula. Delta H equals NH. On its face already, this is a little bit tricky because we have this delta H and also what I always call plain old H, regular H. And they have different names and different units to help us tell them apart. The delta H is the enthalpy change. This is measured in kilojoules, and it could be a positive or a negative value. Okay. It can go by a bunch of different names. It's the enthalpy change. It's the change in energy. It's the change in heat. It's the amount of energy absorbed or released. It's the quantity of energy liberated, absorbed. Watch those language cues to tell you something about delta H. Also, watch your language cues for is the delta H positive or negative? Gain, absorb, endothermic or positive, loss, liberated, freed, released, imply a negative delta H. N, as we're used to, is the moles. Often, we're going to have to do mass over molar mass to calculate the moles. It's going to be pretty special for a question to straight up give us the moles. Finally, H, it's the molar enthalpy. This is expressed in kilojoules per mole. And like delta H, it could also be positive or negative. The two, delta H and H, will always have the same sign. They're both positive or both negative. This H, molar enthalpy, it often has extra qualifiers. It's often molar enthalpy of something. Molar enthalpy of combustion, molar enthalpy of formation, molar enthalpy of fusion or vaporization or reaction, lots of different examples. We can even substitute the word enthalpy for heat. It's the molar heat of neutralization, the molar heat of something. Here's an example. If the molar heat of fusion of aluminum is positive 10.7 kilojoules per mole, how much heat is needed to melt 9.00 grams of solid aluminum? What are we being asked to find? How much heat is needed? How much heat? What's the amount of heat? What's the amount of energy? That means we're trying to find delta H. Please notice that this is about melting. That's a phase change. We're actually talking about a change in bond energy, a change in potential energy. That's not what this question is about, but that's an important theoretical foundation of this idea. Look at those units, 10.7 kilojoules per mole. The wording here is slightly unexpected because we expect molar enthalpy, but this one says molar heat. And there's this qualifier of fusion. Fusion is what's happening when we're melting or actually freezing a substance. Okay, so we're being asked to find delta H. Delta H equals NH. The N here, we have 9 grams of solid aluminum. We were expecting to have to do mass over molar mass, and here we are going to have to do that. Think about your own personal preference. Would you be the kind of person who would want to separately use this formula first and then take your answer into delta H equals NH? Or would you feel comfortable doing what I'm about to do? Delta H equals mass over molar mass H. This way, our work is a little bit more condensed. We can be a little bit more efficient, and turns out I think we're more likely to not make a mistake. Let me substitute. This lowercase m is the mass of the aluminum. I have 9 grams. 9 grams of aluminum. So now I need the molar mass of aluminum as well. I can look it up in the data booklet. I don't have to remember. I can always find it on the periodic table. The molar mass of aluminum is 26.98 grams per mole. We're going to take this and multiply it by H, the molar enthalpy, here being called the molar heat of fusion. It's a positive number. It's 10.7 kilojoules per mole. That's it. I can get to my calculator and see what we get. Let me take my time. 9 over 26.98 multiplied by 10.7. My calculator gives me a raw answer. It's 3.5693106. I like to call this my raw answer. It's what the calculator is telling me. I have to finish it off. It's the answer, but it's raw. What about my significant digits? What about my units? There's two numbers in the question, each with 3 significant digits, so I'm rounding off to 3 digits. That 9 rounds up. This is 3.57. Because I'm finding delta H, I expect kilojoules. Let's look at what happened in the units. Here the grams cancel, the moles cancel, and as expected, we're left with kilojoules. I really like this extra step at the end. Have a moment of reflection about should the answer be positive or negative. We're starting with 9 grams of solid aluminum. We're going to melt it. To melt it, we have to put energy in. We have to increase the amount of energy to get it to melt. That's an endothermic process. So here I have a positive answer. It all makes sense. A style of question we're going to encounter is enthalpy change. It has a really important theoretical foundation. It's about potential energy. Really watch your H versus delta H. It can be a little bit confusing. We really want to work hard to keep those organized. Watch out for keywords that are going to give you signals about positives or negatives. Watch out for language. It's going to tell you H, molar enthalpy. We should expect that we're going to do mass over molar mass a lot too. Here I found a way to take those formulas and combine them together. And I hope that helps.